Thank you very much, Matthew, for the introduction, and thank you very much for having me to present today. It is my pleasure, and today I will present about ENSO IoT and the innovation through flow, the interactions and future projections. And I am based at Climate Change Research Centre, University of New South Wales in Australia. And this work is a compilation of our work that involved many collaborators, including Wen Zhuchai, Mike McFadden, and Guojian Wang, and there are many others. And I'll start off my presentation with, can you see my slides here?
Yes.
So, yeah, I'm based in Australia. So, and Australia is clearly impacted by the El Nino Southern Oscillation, ENSO. And for example, in 1983, we had very big drought, and the condition was very dry. The dust storm in Melbourne, and in 2011 there was a strong La Nina, and Queensland was suffering in flood. And in fact, this year has been a back-to-back La Nina since last year, and there was catastrophic flooding, and that actually impacted many people in Queensland and New South Wales regions, and we had commentaries on the conversation, as you can see in the slide. and here, just put on my laser pointer. And this study here, we show that a lot of moisture come from the Coral Sea during La Nina, and we had also easterly flows coming from the Pacific Ocean into inland, driving lots of rainfall. In fact, the rainfall has been record-breaking over this region. And of course, in Australia, there are so many processes impacting the rainfall, but ENSO and IoT are here, which is a big driving factors, and this is what I'm going to talk about today. And we know that the IoT Indian Ocean Dipole has a big impact, not just in Australia, but also in China and the Indian monsoon rainfall as well. For example, the 2019 positive phase of the IoT was very strong. In fact, it was the first, extreme positive IoT this century. And it actually promote very dry condition over southeastern Australia, and we had a severe bushfires, which claimed many lives, 26 just in New South Wales alone, and $6 billion of damages, with more than 2,000 homes destroyed. And El Nino and La Nina impacts many regions across the world. This is a picture taken from this ENSO book, chapter 16 by Lisa Goddard and Alexander Gershunov. As you know, it has impact over southwest US and in South America as well. And when we have a El Nino, for example, we have drying over northeast South America and wet in the southeast. Okay, and the impact of ENSO is just not limited in rainfall, but also extends to marine heat waves. For example, here in Ningaloo Nino 2011, it coincided with a strong La Nina. It intensifies currents coming from the north through the Indonesian through flow, and it caused a massive heat wave with temperature above 5 degrees Celsius. So there was coral bleaching and those kind of things. So I will talk about a little bit more about ENSO and IoT and Indonesian through flow, and before going into the future projections of ENSO and IoT, and then I will end presentation with a recent study on Indonesian through flow. Okay, so what is ENSO? As many of you know that during La Nina we have stronger trade winds, and that pulls water towards the maritime continent, and that drives convection. But also the sea level here during La Nina is increased. What it means is that it drives a pressure gradient so that the Indonesian through flow, which is current coming from Pacific into the Indian Ocean, is enhanced. El Nino is opposite. You have a weaker trade winds, it's a decreased sea level in the maritime continent, thereby reducing the Indonesian through flow, the ITF. In a positive IOD, it is also associated with a weakening of the water circulation. So there's a subsidence over the maritime continent, and what it does is it reduces the sea level in the Indian Ocean side. So that increased the ITF. This book chapter has more information about the impact of ENSO and on the ITF, if you want to read further. So El Nino and positive IOD tends to occur together. If you correlate Nino 3.4, which is a measure of ENSO, and the dipole mode index, which is a measure of IOD, you get a positive correlation. And the IOD tends to lead ENSO by about 2 to 3 months. That's black is in a reanalysis. And here all the colored lines are for CMIP 5 models. And there's a bit of difference in the lab. And I will talk about that towards the end of the seminar. So El Nino tends to occur with positive IOD. And as you remember from the previous slide, El Nino is corresponding with a reduced ITF, but the positive IOD corresponds with an enhanced ITF. Therefore, you can think like there's a competing effect on the ITF. So if we correlate ENSO with the ITF total, so integrated transport across depth, El Nino corresponds with a reduced ITF. But with the Indian Ocean dipole, there's not much correlation. There's the correlation is all over the place for the models. So it's not clear, but it does not mean that the IOD does not impact the ITF. For example, some individual IOD events, the impact is clear. For example, in a study by Kandaga, Pujiana, found that 40% reduction in ITF transport during the week 2016 La Nina was due to concurrent negative IOD. And just quickly mention, we're also interested in El Nino La Nina because ENSO is arguably the most predictable phenomenon in the world, climate phenomenon. And thanks to this discharge and recharge component of the ENSO, it is actually quite predictable about 3 to 6 months in advance. And in fact, ENSO is also a source of predictability for the IOD as well. So as during El Nino, it leads to a discharge, and then it leads to a La Nina because it's cooler. And then during La Nina, the system starts to recharge and promote El Nino. And the amount of water above this thermal line is called the warm water volume. And if we quickly look at this plot, so the colored squares are the ENSO outlook this is the Australian Bureau of Meteorology ENSO outlook, and it tracks pretty much well with the warm water volume shown in black. So it's quite fascinating actually. Our prediction system is actually somewhat tracking the warm water volume, and the green one is Nino 3.4. So when it hits certain threshold, it will trigger this warning. It's alert or event. So it's for the 2015 El Nino. The evolution was quite confusing in 2014 because we had a spike in the warm water volume and then it triggers an alert. But in fact, the warm water volume is dissipates for a while and then increase again. And this actually highlights the challenging factor in our ENSO prediction. And that partially stems many factors, right, causing this prediction challenges. But one of the source of this challenge is the fact that ENSO events come in many flavors, and it is basically a decomposition of superposition of two modes. First is the classical cold time mode, and second is the east-west mode. So if you do an EOF on SSD anomalies and plot the Pc1 versus Pc2 digital component, you can see that the strong El Nino is basically Pc1 plus Pc2. So it becomes, if you superpose these two patterns together, you get an Eastern Pacific El Nino. That's what the big ones, like 1982 and 1997 and 2015 as well. And the strong La Ninas will be the opposite of these patterns. It will be Central Pacific La Ninas. These are big ones. And this actually underpin the nonlinearity in the ENSO system in the Pacific. So if we look at the skewness of SST anomalies, in the Nino 3 region, the skewness is strongly positive, and in the Central Pacific Nino 4 region, it's negatively skewed. So if we remove the ENSO extremes, you can see how the skewness reduced. And this kind of Indo-Pacific SST anomalies profile, this underpins the ENSO nonlinearity and asymmetry. And this feature is important for understanding how ENSO can change in the future. And of course, Eastern Pacific and Central Pacific events, they are not just the terminology, but in terms of impact, they are quite different. For example, in Australia, the impact is actually stronger during Central Pacific El Nino. It's more widespread across the continent. So to understand what's going to happen in the future, of course, we have to use climate models, and climate models have evolved through many generations of models as organized by CMIP 1, 2, 3, 5, 6, and we are now in the CMIP 6 stage. And these models, of course, are forced by increasing greenhouse gas concentration. And we can use this model because these models can actually simulate ENSO. For example, in this paper, we show that the patterns are quite reasonable overall across models, although there are many, the intermodal diversity is quite large. But yes, we can use climate models to project what's going to happen in the future, although we have to be cautious about it. So what is the current status of ENSO projections? So back in 2010, well, about 10 years ago, everyone says that ENSO is not going to change the future because all these climate models are not in agreement. There's basically no intermodal consensus. That is based on, for example, looking at standard deviation of 3.4, which is the classical way of looking at and measuring ENSO. So then people start looking at other things. How can you not see anything when the mean state changes are clear? For example, the local separation weakens. So we're looking at all these processes, especially the nonlinear processes, because those are processes that are important in defining extreme ENSO events. So in this review paper 2015, the conclusion was that yes, we can see changes in ENSO, but not looking at surface temperature variability at certain points, but in terms of the nonlinear processes. Okay, so I just talked about that, and some in a way we cannot see changes in the ENSO SST variability because there are competing feedbacks. So the ENSO consists of positive feedback, and that tends to increase, but also the damping feedback, the thermodynamic damping also tends to increase as well. So they are compensating. Therefore, you don't see changes overall. And this despite clear change in the mean state. For example, there's a weakening of local circulation and of course the currents also weaken, and importantly, the surface ocean is warming faster than the deeper ocean, and that has a big implication on how ENSO operates in the future. And maritime continent also warming faster, and that can promote stronger trade winds in this region, and that can cause extreme La Niñas. So just quickly, looking at the nonlinear processes, we can find that there's more increases of eastward propagating El Nino events because it bites through the mean currents, and the mean currents are projected to weaken, and that is easier to move temperature anomalies from west to east. And based on rainfall as well, if we look at the rainfall in the Eastern Pacific, the extreme El Ninos show a very large rainfall, and because in the future the Eastern Pacific warms faster than the rest of the region, then it promotes atmospheric convection, which are favorable for extreme El Ninos to form. So there's an increased frequency in extreme El Ninos. And for La Niñas, we can actually look at the sea surface temperature variability in the Central Pacific. And yes, we can see, as I mentioned before, the maritime continent warming actually promotes nonlinear feedback processes to kick in the Central Pacific, which are favorable for extreme La Niña to form. And all these studies are based on model selection, because when we look at these nonlinear processes, not all climate models can simulate this nonlinear property. So we have to select models that can produce this kind of processes. So this plot here summarizes what I just said. This is based on CMIP 5 models. If you look at the Nino 4 region, which is blue box, and the Nino 3 red box, you can see that there's no intermodal consensus. This is the difference in standard deviation of SST between future minus present day. So gray shows that it's not increasing, while if it's not gray, it's increasing. This is for each of these are different models in CMIP 5. But if we look at rainfall for each grid point, you can actually see a strong intermodal consensus. Therefore, the message here is that it doesn't really matter what the SST is going to change, but the rainfall response to ENSO variability is going to change. This is actually the process based on the nonlinear processes governing this ENSO. So, in fact, when we say that there's no change in the SST variability, this is not quite precise, because if we look at the SST variability, but then we can actually decompose into a Eastern Pacific type and Central Pacific type. And as you remember from previous slides, there's a nonlinear relationship between Pc1 and Pc2. This is the invert of what I showed before, but that's basically the same. So we should select models that can capture this kind of nonlinearity, right? And we discard all those models that can't, because if the Pc1, Pc2 look like this, then it does not capture the skewness in the Eastern Pacific and the negative skewness in the Central Pacific. So let's get rid of those models. And this still, in fact, underestimate the extent of the nonlinearity in the observations, which is, I believe, there's the black one, ops, right? We can measure the curvature of this relationship, which is indicated as alpha. So if most models, many models show 50% of the strength of the observed alpha, and we use those models to look at what's going to happen to ENSO in the future. And it turns out that when we use these models, the Eastern Pacific ENSO is actually, the variability is enhanced. Most of the models showed red is a future and blue is in the present day, and most of them show an increase in the variability. And this increase actually manifests in the number of strong El Nino events. It's shown in this bottom panel. And this, the multi-model mean the difference is really statistically significant. And how does that arise? It's because the surface ocean is warming faster than the deeper ocean, and this actually promotes stronger acid coupling. And if we plot the change in ocean stratification versus the change in the E index, which is the Eastern Pacific ENSO index, then there's a strong correlation. Okay, so this is a later review paper that we had. It's published last year. Even if you look at observations, so you can look at different reanalysis. I think here, this plot here is based on 5 reanalysis products from 1900 to 2020. You can see how the E index, which is quite highly correlated with Nino 3, is increasing in variability after 1960. You can see that, right? The standard deviation was 0.68 for Nino 3 post pre-1960, and it's 0.85 post 1960. And even in the Central Pacific as well, which is highly correlated with Nino 4, the standard deviation increased pre and post 1960. And yes, and this characterized by more extreme El Ninos, the E index, and more extreme La Ninas for the C index. This is what the picture looked like for extreme El Nino, which is basically more Eastern Pacific warming, while La Nina is more Central Pacific cooling. Okay, so what does the model show? This is now based on CMIP6. Again, it confirms the finding from the previous study based on CMIP5 and CMIP3. But in this case, the intermodal consensus are actually stronger. The future projections, if we select models based on that nonlinear relationship, there are 23 CMIP6 models indicate increased EP variability. So all of them, 100% intermodal consensus. As well as 65% generate an increase in CP variability. Even without selection, if you don't select models, the majority of CMIP6 models generate an increase in Nino 3 and Nino 4 excessive variability with 28 and 27 out of 34 models. But if we use CMIP5, there's less in the model consensus. And that message is emphasized in this brief communication, saying that even if we use Nino 3.4, just forget about the E index and C index. In CMIP6, the intermodal consensus is actually very strong. Yeah, so this is in different scenarios. SSP 585, which is a strong emission scenario, and even in 126, SSP 126, there's a strong mitigation under Paris Agreement, and we can see that the Nino 3.4 variability change is actually stronger in the future under all these scenarios. It's somewhat actually different to what IPCC said in the ARC6 report, saying that there's actually intermodal consensus in terms of rainfall, but no intermodal consensus on excessive variability. But this latest research, the message is not really captured by the AR6 because it's quite new. Okay, so we think that it's because CMIP6 has improved overall in terms of ENSO, although not much. And for example, in this study by Young Planton, they found that the tropical Pacific time mean is actually improved. The seasonal cycle, the ENSO patterns, diversity, and remote teleconnections are somewhat improved. Just For example, the gold-tongue bias in CMIP 5 here is quite strong, but in CMIP 6, it's actually reduced. So yeah, so I think all this improvement, not improvement, I mean the increase in the model consensus could stem from improvement in these models, less bias. Okay, so with Indian Ocean dipole, it's somewhat a similar message. Earlier on, we did not see a change in terms of the dipole mode index, which is the measure of IOD, Western Indian Ocean SS anomalies minus anomalies in the Eastern Indian Ocean. But then in terms of nonlinear processes, here in this paper is based on rainfall process, we can see in fact that the extreme positive Indian Ocean dipole is increased in frequency, and that is tied to the mean state where weakening Walker circulation is associated with a warming of the Western Indian Ocean, and it promotes convection. Therefore, moving convection that happens in the east towards the west. And in this later study, which was published last year, I believe, we look at SST anomalies. Again, we can see, in fact, the change happen in the SST anomalies, but not in terms of the DMI. If we look at models, so purple is CMIP 6, black is CMIP 5. The intermodal consensus is not great, and in fact, the change in the DMI, standard deviation, is not statistically significant between present day and future. And again, we select models, right? And the discarded models also, in fact, show, poor intermodal consensus. And the DMI itself is quite interesting. It can be, it contains it captures SST patterns, somewhat like what ENSO happens with ENSO, where you can separate into two different modes. Here we can separate into strong index and moderate index. Just tell you about it in the next slide. So if we do an EOF on SST anomalies in the Indian Ocean, the first mode is capturing this dipole pattern, the quite familiar one, warming in the west and cooling in the east. That's the first principal component, number one, and that is highly correlated with the DMI. The second mode is cooling over the Eastern Indian Ocean. And if we, yes, so that pattern here is then an IOD. It's not quite. It's not quite a dipole. It's a cooling in the Eastern Indian Ocean. And if we superimpose these two, you can see how the 1997 extreme IOD 2019 is in fact an addition of these two patterns, right? You get a strong cooling over the Eastern Indian Ocean and somewhat less of a warming in the Western Indian Ocean. On the other hand, the weak or moderate positive IOD events like 82, 2015, 1987, you subtract the EOF2 from EOF1, so you have less cooling in the Eastern Indian Ocean, and what you have remaining is the Western Indian Ocean warming mostly. So we can have a S index and M index, right? Pc1 plus Pc2 for S index and Pc1 minus Pc2 for M index, and you can look at the change in the standard deviation between present day and future. You can see how for the M index is actually a reduction in the variability in the future, while in the S index is a stronger variability in the future, and the intermodal consensus is high. And how does that happen? We found that it's not due to what happens in the Pacific. If you remember from the first slide I showed, there was a high correlation between ENSO and IOD, but somehow when ENSO gets stronger in the future, it does not really translate to stronger IOD in the future. Instead, it is it comes from the change in the mean state within the Indian Ocean itself. So we found that the Western Indian Ocean warming is actually governed by Ekman pumping. And in the future, this Ekman pumping term is actually gets weaker. And that is due to a weaker response of the wind variability to SSE variability. And that is probably because the troposphere, the lower troposphere, is actually warming faster than surface ocean. So the atmosphere becomes stable under global warming. So the wind does not respond as much to SSE variability compared to present day. And for the strong index, the strong IOD, positive IOD, it is tied to the mean warming pattern at surface. So there's warming of the Indian Ocean and cooling in the east. So as I said before, it promotes convection to move from the east towards the west. So that is enhancing the easterly wind anomalies in this region, in the eastern Indian Ocean. And the intensity of this SSE warming pattern has a strong correlation with the change in the strong positive IOD in the future. Okay, so all these projections, answer and IOD projections, have an impact on the Indian Ocean, Indonesian true flow. And in this study, we used 20 CMIP5 models and a SOTA reanalysis to study what, basically trying to investigate, because we don't really actually know much about Indonesian true flow variability in climate models, although observations have provided us with a lot of useful information. So this is somewhat a first study looking at different models, how they perform in simulating Indonesian true flow. Just start off with future projections. In the mean state, we can see that the ITF transport actually weakens in the subsurface. At the surface layer, there's not much intermodal consensus. And if we look at separate into two layers, surface layer and the deeper layer, surface, by what I mean by surface is between 0 to 100 meters, and subsurface is 100 to 300 meters. There is actually a strong intermodal correlation between the change in ENSO between present day and future and the change in the ITF variability at subsurface. And there's not much correlation at surface. Similarly with the IOD as well, although the ENSO has a much stronger intermodal correlation, and I will talk about it next. So if we want to look at how ITF variability change in the future and in terms of ENSO and IOD impact, we should look at what's happening at the subsurface, not at the surface. So here's an intermodal correlation between 3.4 standard deviation in the present day and the surface ITF variability and subsurface. And we do the same with the DMI. And we can see how the DMI variability actually impacting IOD Indonesian ITF amplitude more at the surface, while ENSO has an impact at the subsurface. And that comes from the fact that if we composite ITF transport variability based on El Nino and positive IOD, you get this structure, special structure. Bottom is for SOTA analysis, and top is for the CMIP5 multimodal mean. And when we have an El Nino, we get a weakening. Blue is for weakening of transport at subsurface and strengthening at the surface. But for positive IOD, you can see how the transport is actually more prominent and it's deeper as well, but less prominent in subsurface. Similar pattern also can be seen for La Nina and negative IOD, but here we can see more asymmetry, and I'm not going to go into detail in terms of the asymmetry. What is interesting to notice is that at the surface, the CMIP5 models show a prolonged enhanced surface transport, at the surface compared to SOTA. In SOTA, you can see how the subsurface weakening of transport actually propagates upward by the following year. But here, the strengthening of the transport is actually, sorry, the reduction of the transport is actually delayed at the surface, and that is tied to how this transport enhancement at the surface in simplified models is protruding, is prolonged into the following year, and that is tied to biases in the ANSO and IOD in the model. Okay. So overall, we can say that based on these patterns, ANSO has stronger impact on subsurface transport, while IOD on the surface transport. And we can do a UF analysis on this particular structure of transport variability. And here we look at the first two modes. The first mode, black is for soda and red is for the multimodal mean. It shows a surface enhancement, surface intensified transport anomaly, while EOF2 is a dipole. It's an enhancement at surface, but a weakening at subsurface. So let's just talk about the second mode first, because for this mode, the simplified models and SOTA are in agreement. So, and that this particular structure is correlated with ANSO and IOD, both of them. Based on we have an El Nino, we have this pattern as in agreement with what was shown in the composite patterns previous slides, and IOD as well. And if we correlate this principal component with a heat content anomaly, which is the average of temperature above 300 meters, and the surface winds, we can see how it shows a divergence in surface wind, divergence anomalies. So you have a subsidence of a maritime continent with easterly anomalies in the Indian Ocean and westerly anomaly in the Pacific Ocean. So that drives this is an El Nino pattern. It drives lower sea level in the Western Pacific Ocean, and what correspondingly, because of this wind anomaly, you have a lower sea level in the Indian Ocean side. It happens both in simplified and SOTA. But for EOF1, this is interesting because the models and simplified models and the reanalysis, they are not in agreement. In fact, in SOTA, this particular pattern is associated with an El Nino. You have an so it's negatively correlated. Okay, so when we have El Nino, it leads to a weakening of in surface intensified weakening of the structure. But in the simplified model, it's not clear. Instead, it is correlated with the IOD. So when we have an IOD, a positive IOD, it corresponds with a increased transport towards the surface. So if here, the pattern is clear here. If we correlate this principal component with heat content and winds, you can see in CIMIP 5, it is associated with what's happening within the Indian Ocean. Nothing's happening in the Pacific. While in SOTA, it is a response to La Nina. When we have a La Nina, the Western Rossby waves, the Rossby waves from Western Pacific going to the Indian Ocean along the Australian coast. So with this kind of structure. Okay, so models which simulate a stronger EOF1 than EOF2, it tends to have a weaker influence of ANSO on the ITF variability. So this kind of bias means that the ANSO has less influence on the ITF variability in those models. And in terms of the IOD, as we know, current models have a strong IOD bias. It's too strong. And when the IOD is too strong, the surface winds over the Indian Ocean are also too strong. So the prevalence of the IOD on the Pc1, on the first mode, the surface intensified, is because these winds are too strong. So it hence lots of carbon transport into the Indian Ocean, thereby strengthening the Indonesian true flow stronger than what it should be. And this is not the end of it, because there's also another bias whereby when we correlate ENSO and IoT, in the reanalysis, IoT is actually leading ENSO by a few months. But in the models, ENSO actually leads IoT by a few months. So that's the opposite. And that is not because of too much on IoT simulation. It is too strong, but it is more related to ENSO teleconnection. So when we have an El Nino, it tends to induce positive IoT in the following months into the following year. And so this delayed bias is actually causing problem in the models. When the ENSO leads IoT, the longer it leads, it tends to have it causes the ENSO to have a less influence on the ITF variability at the surface, because the IoT and ENSO have a competing effect. So that actually contributes to weakening of the ITF variability in models. And this should have implications on, for example, marine heat waves. It could be underestimated in models. So just to summarize my talk, the current future projections actually point to increased ENSO and IoT variability. And so we want to have a more accurate future projections, and to do that, we need to understand better the ENSO and IoT nonlinearity. And we showed before, this will be done through understanding Eastern Pacific and Central Pacific ENSO and strong and moderate IoT events. And of course, we need to reduce model biases. And all this can have an impact on many other things in the current system. And I've shown you here in this example is for the Indonesian true flow variability. In this case, considering the physical structure of the true flow is actually necessary to identify the impact of ENSO and IoT in the future. So I should end my talk here. If you have any questions, please go ahead. Thank you.